Okay, this is wastewater treatment certification training, Chapter 5, Part 3. More on physical and biological treatment processes. In Part 3 of Chapter 5, we're going to cover biological and chemical treatment for the removal of nitrogen and phosphorus, and we'll cover secondary sedimentation, or the secondary clarifier. For biological removal of nitrogen, requires two steps. First step is a nitrification step, where the ammonia nitrogen is converted into nitrates, and then denitrification is where the nitrates then are broken down into nitrogen gas and CO2. To convert ammonia to nitrate, ammonia is NH3, nitrate is NO3. It's an ion, so it's got a negative charge. This step requires high levels of dissolved oxygen. It takes 4.5 parts per million of oxygen to convert 1 part per million of ammonia to nitrate. So if you're trying to nitrify in your plant, at the area in your plant you are nitrifying, you must run your DO at higher levels. Factors affecting biological nitrification: your organic loading, food to microorganism ratio, your solids retention time, MCRT or sludge age, alkalinity, pH, toxic materials, dissolved oxygen, and of course, temperature. Denitrifying bacteria use carbon dioxide rather than organic carbon for the synthesis of new cells. Nitrification requirements: the organic loading, it's 10 pounds of ammonia per 1,000 cubic feet per day at 2,000 milligrams per liter mLVSS at 10 degrees C, that's 50 degrees F. Your solids retention time or sludge age: sludge must be greater than 10 days old for the nitrification process to begin. So it takes older sludge. Alkalinity: you need 7.2 parts per million of alkalinity needed to convert 1 part per million of ammonia to nitrate. Typically, if a plant is having an issue removing nitrogen from their wastewater, they need to check their alkalinity and add caustic soda or something to their plant to increase the alkalinity. The optimal pH range for nitrification is 7.8 to 9.0, but systems can adapt. These bacteria can adapt to lower pH conditions, and you can get adequate nitrification at the 6.8 to 7.2 pH that's recommended for BOD removal. You also have to be free from toxins. Nitrifying bacteria are more sensitive to toxins. They will be killed quicker, and they are also more slow to multiply. So you need to really control anything that's going to kill the nitrifying bacteria. You should keep your dissolved oxygen at 2 to 3 milligrams per liter in the nitrification step. Your temperature, as we always see, temperature at 2,000 milligrams per liter of mLVSS at 10 degrees C, you can only treat about 10 pounds of ammonia per 1,000 cubic foot. At 20 degrees C, warmer temperature, that goes up to 25 pounds of ammonia per 1,000 cubic feet. Denitrification is the reduction or conversion of nitrate ions to nitrogen gas. This requires anoxic conditions in your tank. That's less than 0.5 milligrams per liter dissolved oxygen, but not 0. The bacteria use nitrate, not oxygen, in the process of making energy. Low levels of carbon often occur, or food often occur at this step, and sometimes you need to add carbon, usually in the form of methanol, to make sure you're getting proper denitrification. You don't add a lot. You want to make sure you keep your BOD in control. Denitrification should take place in the aeration tank of activated sludge plants. You should take place at the end of your aeration tank. If it takes place in the secondary clarifier, the following may occur. You'll see bubbles of nitrogen bubbling to the surface in your clarifier. What these bubbles of nitrogen will do is they will cause the sludge blanket to start rising in the tank and can push solids over the weirs. You could be out of compliance with total solids. This is kind of what happens. Here's a settleometer that they let sit, and you see how the sludge blanket is lifted off the bottom and is at the top of the liquid now. If that was in your clarifier, those solids would be going over your weir and into your effluent. To reduce denitrification in your clarifiers, you need to achieve denitrification in the preceding biological units, which are your aerated units. You can reduce MCRT, sludge retention time, or sludge age in the aeration basins by increasing sludge wasting. But if you if you reduce it too much, you will also reduce the nitrification, and you won't be removing your ammonia effectively. You want to keep the clarifier influent DO greater than 2.0 parts per million. Avoid long clarifier solids retention times. Again, waste frequently, small quantities. Keep the sludge blankets less than 3 feet deep. And keep your return activated sludge rates as low as possible. Phosphorus removal, it can be biological or chemical. Why do we worry about getting rid of phosphorus? It's one of the major nutrients contributing to eutrophication of lakes and streams. The other one is just what we talked about, nitrogen. Eutrophication promotes excessive plant growth in water, and as those plants die, the decay leads to decreased levels of oxygen. To remove phosphorus in your wastewater system, it increases treatment costs for the wastewater plant, but also in the drinking water plant when the water goes to that plant. Phosphorus in municipal wastewaters. Each person contributes 0.0048 pounds of phosphorus per person per day. That's one of the population equivalents you talked about in chapter 3. Normal influent contains 5 to 20 milligrams per liter of phosphorus. This is municipal influent we're talking about. All bets are off if you're in the meatpacking industry or anything like that with a wastewater plant. 1 to 5 milligrams per liter of the influent is organic phosphorus. The rest is normally inorganic. Reduction of phosphorus as in detergent has really helped, but it's still in use in agriculture as a fertilizer, And during runoff from the fields, you can get into the water. Biological removal is accomplished through the use of phosphorus accumulating organisms, PAO. The principal advantages of biological phosphorus removal are reduced chemical costs and less sludge production as compared to chemical precipitation. Phosphorus in the influent wastewater is incorporated into the cell biomass, which is subsequently removed from the process as a result of sludge wasting. The reactor configuration consists of an anaerobic tank followed by an activated sludge tank. Under anaerobic conditions, the PAOs will reproduce, and they have a competitive advantage over the other bacteria that need to have oxygen to reproduce. Here is a typical system, an activated sludge plant. Your influent is mixed with the activated sludge. It goes into an anaerobic reactor, a mixing tank, very low DO, close to zero. And your retention time in that tank is about 30 minutes to 1 hour. That allows the PAOs to reproduce and grow. Then as they go into the aeration tank, they have a competitive advantage over the other bacteria. They absorb the phosphorus, then they're settled out in the sludge. When you waste your sludge, you're also getting rid of the phosphorus. In oxidation ditches, they can be programmed for nutrient removal. As the wastewater comes in, it comes into an anaerobic zone. Again, to give the PAOs a chance to reproduce and to grow. Then they hit the aerobic zone. The brush is putting oxygen into the air. Then after it has time to nitrify, they'll go into an anoxic zone where the DO is 0.5 or less. This will allow denitrification to occur. Nitrogen gas bubbles out the top. As it goes to the end of the ditch, it goes to the clarifier. When you waste the sludge, you get rid of the phosphorus that the PAOs have accumulated. You have to have anoxic zones to allow for the denitrification to occur and anaerobic zones to allow PAOs to grow. The same with sequencing batch reactors. You change the setup a little bit. You have a mix and fill with no aeration. Then you continue the stir as an anaerobic stir. You're not putting any air or oxygen into the system. Again, for about 30 minutes to an hour. Then while stirring, you start adding air to cause nitrification and to get rid of BOD. Then you stop the addition of air, continue stirring, and allow the mix to go anoxic, less than 0.5 part per million of DO. After that, you let this, that will allow denitrification to occur. Then you allow the tank to settle, decant the clear water to your next step. So oxidation ditches and SBRs are very good for allowing nutrient removal. Chemically removal of phosphorus. Most commonly used metal salts to take out phosphorus are calcium hydroxide or hydrated lime, aluminum sulfate or alum or aluminum polymers, and iron chloride and iron sulfate. These are all coagulation or precipitating agents. They allow things to precipitate. With calcium salts, the lime reacts with the neutral alkalinity in the wastewater to produce calcium carbonate, which removes suspended solids. excuse me, as the pH of the wastewater increases beyond 10, excess calcium ions then react with the phosphate to precipitate hydroxyapatite. The lime dose required is usually 1.5 times the alkalinity as calcium carbonate, which typically averages 100 to 125 milligrams per liter in wastewater. Neutralization by adding CO2 may be required to lower the pH before subsequent treatment or disposal. High pH and more sludge means that lime is not often the best choice to remove phosphorus from domestic wastewater. Aluminum salts, alum or hydrated aluminum sulfate are normally used to precipitate phosphates. The dosage rate required is a function of the phosphorus removal required. It requires a lower pH than lime. Typically, when you're using these salts, you want your pH between 5 and 7. An 80 to 90% removal rate can be achieved at coagulant dosage rates between 50 and 200 milligrams per liter. At dosage rates higher than 150 milligrams per liter, aluminum coagulants can adversely affect the microbial population, especially protozoa and rotifers. However, this reduction in numbers may have little effect on TSS and BOD removal, as the enhanced removal of solids by the chemical precipitation will occur. Iron salts, ferric and ferrous chlorides and sulfates are all used for phosphorus removal. They react slowly with natural alkalinity, and so a coagulant aid such as lime is normally added to raise the pH in order to enhance the coagulation. For iron salts, the pH range needs to be between 6.5 and 7.5. All these chemical treatment methods that we just talked about, remember the downfall is more sludge, more solids are produced. The treatment strategies for chemical removal of phosphorus, you can do it 3 different ways. You can treat the raw or primary wastewater before BOD removal. You can treat the phosphorus during the secondary biological process, so along with the BOD removal, or you can treat the final effluent post-precipitation to get rid of the phosphorus. Treatment of raw wastewater. Here's your treatment scheme. The influent comes in. It's mixed with the coagulant you're using, either lime or the aluminum sulfates or iron. It allows the coagulation to happen. Then, as it goes into the primary sedimentation tank, those solids will come out and go to the waste sludge. Then your effluent from your primary sedimentation tank is mixed with return activated sludge, goes to the aeration tank for BOD removal, then on to secondary sedimentation, and then your clear water goes to the next step, which is usually chlorination. Treatment of raw wastewater, phosphorus is removed with a 90% efficiency, and final phosphorus concentration can be lower than 0.5 milligrams per liter. Only 10% of the lime fed is actually used, if you're using lime, in the phosphorus removal reaction. The lime dosage is dependent on the alkalinity of the wastewater. Co-precipitation, where you're getting rid of the phosphorus at the same time as the BOD. Influent comes in, goes to your primary clarifier, where the sludge is taken out. Then It's mixed with the return activated sludge on its way to the activated to the aeration tank. The coagulant is added at the head of the aeration tank. Therefore, it is reacting with the phosphorus at the same time the bacteria are eating the BOD. Then you come out of that tank into your secondary clarifier. All the solids are the sludge and the precipitated phosphorus are collected in the secondary clarifier where the phosphorus is wasted excuse me, with the chemical and activated sludge. Chemicals are fed directly in the aeration tank or right before it. It's usually iron or aluminum salts are used. Lime is only added for pH correction. Removal efficiencies are lower than with post-precipitation. Excuse me, normally below 85%. Phosphorus concentrations in the final effluent typically are about 1 milligram per liter. Post-precipitation, influent goes into the primary clarifier, solids are taken out, return activated sludge is mixed in, goes to the aeration tank where BOD is removed. Then you go through your secondary clarifier. Then you go into a mixing tank where you add your coagulant. Then you have another clarifier after that tank. You've got to give it long enough mixing for the precipitation to occur in that tank. Then you let the chemical waste settle as sludge in another clarifier, and the effluent goes on to disinfection. Using metal salts, removal efficiency can reach 95%. And phosphorus concentration in the effluent can be lower than 0.5 milligrams per liter. It also helps remove any of the suspended solids that are not captured in the final sedimentation. Disadvantages: high cost for treatment, mixing, and the large settling ponds you need to settle out the sludge. Secondary sedimentation, we're finished with phosphorus and nitrogen. Now we're talking about the final clarifier. It follows the activated sludge process. It works similar to primary clarification process. It's the source of return activated sludge. Excuse me, knowing how much sludge is in the secondary clarifier is important. When you're measuring your sludge blankets in your secondary clarifier using a sludge judge, core taker, or any of the other ways you can measure sludge, you want to measure it 1/3 of the radius in from the edge. So if you've got a 30-foot radius on your clarifier, you want to go in from the outer edge 10 feet to measure your sludge blanket. You measure at the same place all the time so you get consistent readings. You take the sludge judge sample when the sludge rates are at 90 degrees to the bridge. That gives you time to take your sample, get the reading of how deep your solids are, get your sludge judge out of there before the rate comes around and hits the sludge judge. Because if it hits it, it's going to snap it off. Process controls, make sure you have even distribution of flow to all clarifiers if you're using more than one secondary clarifier. If you've got 3 of them, you want the flow to be equal going to all 3 clarifiers. You want to get your return activated sludges flow rates as low as possible. Because the more return activated sludge you add, the more solids you have loading on your clarifier. And you want to maintain a sludge blanket depth in all units at 1 to 3 feet. If things go wrong, check your return activated sludge or your waste activated sludge pumps. Maybe they're not pumping what you think they're pumping due to a clogged pump or an impeller wearing or something like that. Check your sludge collection equipment, the rakes or scrapers that are in your clarifier, to make sure they're not broken. Check the sludge blanket depths more frequently with a sludge judge, sludge core taker, or sludge blanket finder, and check it at other locations in your tank to make sure something's not wrong with your tank. Math for the secondary clarifier: you got solids loading rate. It's used for design and the average and upper limit based on the type of treatment. Settling characteristics affected by the amounts of flow, temperature, and filamentous bacterial growth. There's the typical design information for secondary clarifiers following the type of treatment. So the math for this is solids loading rate. The flow to a 5 million gallon per day oxidation ditch is 3.9 million gallons per day. The MLSS concentration of the oxidation ditch is 3,300 milligrams per liter. The return activated sludge flow is 115% of the influent flow. What is the solids loading rate on 2 clarifiers with a diameter of 150 feet each? Solids loading rate is expressed as pounds of solids per day per square foot of surface area. It's solids applied in pounds per day divided by surface area in square feet. Note that if the solids loading rate is asked for in hours, divide the answer by 24. We'll work through this first one. First, calculate the pounds of solid applied per day. You must calculate all flow into the oxidation ditch. That is your influent plus your return activated sludge flow. So total flow is your influent flow in million gallons per day plus the return activated sludge in million gallons a day. In the case of this problem, our influent was 3.9 million gallons per day. The return activated sludge flow was 115% of that. So you take 115 divided by 100, gives you 1.15. So you take 3.9, your influent flow, times 1.15. That gives you 4.485 million gallons per day of return activated sludge flow. You add your 2 flows together, 3.9 plus 4.85 means you have a total flow going through that system of 8.38 million gallons per day. The applied solids, you know your MLSS was 3,300 milligrams per liter. So it's your flow in million gallons per day, 8.385 times 8.34 times 3,300 gives you 230,771.97 pounds per day are going through that clarifier. We have to calculate the surface area of the clarifiers based on what we gave you. We know these clarifiers are round because we only gave you one number. So the area is 0.785 times diameter in feet times diameter in feet. There are 2 clarifiers, each with 150-foot diameter. So the area is 0.785 times 150 times 150 times 2, because there's 2 clarifiers, which gives you 35,325 square feet. Your solids loading in pounds per day per square foot is 30,771.97 pounds per day, divided by 35,325 square feet. That's your surface area. And you get 6.53 pounds per day per square foot. Make sure you take your flow plus your return activated sludge flow when you're doing this. Here's one that you all can work out. The flow to a 4.5 million gallon per day oxidation ditch is 3.1 million gallons per day. The MLSS concentration of the oxidation ditch is 3,100 milligrams per liter. The return sludge flow is 75% of the influent flow. What is the solids loading rate on 2 clarifiers with a diameter of 100 feet each? Go ahead and work this out. I'll give you some time, then we'll come back and work through it together. Okay, how did you do with that math problem? What did you find for the solids loading rate on the two clarifiers in the problem? Correct answer, 8.93 pounds per square feet or square foot. Let's see how we do it. Solids applied. First thing we've got to do is find our flow. Our RAS flow is 3.1 times 0.75. Our influent flow was 3.1. So our return activated sludge flow is 3.1 times 0.75, which gives you 2.325 million gallons a day. We add that to our influent flow of 3.1, means total flow to the clarifiers is 5.245 million gallons per day. We calculate the pounds formula. The flow is 5.425 million gallons a day times 8.34 times 3,100 milligrams per liter. That was the concentration given in the problem. Means you're adding 140,258 pounds of solids. Your clarifier area is 0.785 times 100 times 100, which is 7,850 square feet, but there are two of them. So your total surface area is 15,700 square feet. 7,850 times 2. So your solids applied, 140,258 pounds of solids divided by 15,700 square feet of clarifier gives you a solids loading rate of 8.93 pounds per square foot. And that concludes Chapter 5, Part 3. If you have questions, you can send them to envhelp@ky.gov or call 502-782-6189, and your questions will be forwarded to a trainer who will get in touch with you and show you what's going on.